students. I'm Neeraj Gupta again, and we are having this series of video lectures on electrical measurement and instrumentation, core subject of electrical and electronics engineering. And today's topic is from first unit. We are going to discuss about the analog measurements of electrical quantities. So here will be the contents of this lecture. The basic introduction, then types of measuring instruments, then essential requirements like deflecting torque, controlling torque, then the description of these two methods with respect to the controlling torque, then damping torque, their air friction and eddy current, and one more is the fluid friction damping. So then after we will move to PMMC instruments, then MI instruments, attraction type, repulsion type. Further we will move to dynamic electrodynamic instruments. Now, as far as concerned with the introduction of this topic, we will be basically looking for the quantities which are analog in nature. Analog in nature means where output could be defined for every instant of time. So the measurement of a quantity is a result of comparison to the quantity from a defined standard. The instruments which are basically used for the purpose are called the measuring instruments. With the introduction of the instruments in the circuit conditions should not change. The power consumption should be minimal with these instruments so that there will be no loss of signal. So these should be some specific characteristics of the measuring instruments. Now, what type of measuring instruments do we use? We use basically three types of instruments. One is simply that are indicating the value of the quantity which is being measured. Second are which could record the value, that is recording instruments. And third one are integrating type instruments, which will be accumulating the reading over a span of time. So examples of indicating instruments could be a simple scale, which will be directly giving you the reading of the displacement or the length. Then recording instruments could be a digital storage oscilloscope. Then integrating instruments are, example of this is a household energy meter. That is recording the kilowatt hour readings over a span of month so that your bill could be generated with the help of that. So these are simply using a dial and a pointer to show or indicate the magnitude of the measuring quantity. So these are called as indicating. Instruments give a continuous record of the given electrical quantity which is being measured over a specific duration. Then integrating instruments measure the total quantity of electricity which is delivered over a period of time. That is household energy meter. Now, for measuring instruments that is of this mechanical electrical MEMS type, mechanical electrical measurement structure, that is deflecting torque, controlling torque, and damping torque, or we specifically call it also the restoring torque. The deflecting torque is used to measure the deflection with the help of the quantity which is being measured, and then controlling torque is to control that torque, and to restore its position we use the damping torque. So as far as concerned with the deflecting torque, the description for this could be deflecting torque causes the moving system and the pointer of the instrument to move from its zero position. Production of the deflecting torque depends upon the type of indicating instruments. The deflecting system uses one of the following effects. It could be using magnetic effect, could be using thermal effect, it could be using electrostatic effect, or the induction effect to cause the deflection. So the magnetic effect is when a current carrying conductor is placed in a magnetic field, it experiences a force which causes the move the pointer. For example, the moving iron attraction and repulsion type of instruments and the PMMC instruments are the example of this, using this magnetic effect for produce the deflection. Then thermal effect are the current which is to be measured is passed through a small element which heats it and causes a rise in temperature, which is converted to an EMF using a thermocouple which is attached to it using a Seebeck effect. Then electrostatic effect. When two plates are charged, there is a force exerted between them which moves one of the plate and causes the reflection. Then could be induction effect. When a non-magnetic conduction disc is placed in a magnetic field, it produced by the electromagnets which are excited by alternating currents, a EMF is induced in that. The example of these are energy meters. Then comes the controlling torque, which basically compensates for this deflecting torque. The controlling torque limits the movement of the pointer. If simply deflecting torque will be applicable only, then the pointer will keep on deflecting. But to control that, the controlling torque is provided. It limits the movement of a pointer and ensures that the magnitude of the deflection is unique and is always same for a specific value of electrical quantity to be measured. So that is the purpose of this controlling torque. There are two methods for this. One is using a spring control method. Another one is for gravity control method. So if we talk about the spring control method, there are two phosphor bronze spirals, springs, A and B, are attached to the spindle, to the moving system of the instrument. They are wounded in opposite direction. The pointer is attached to the spindle. Here, at this point, the pointer is attached over here. And when it moves, it tries to restore its position. These springs try to restore its position. And as it restores, the amount of deflection or deflecting torque which has been implemented on that is counterbalanced. So this is a calibrated scale. This is balance weights, control spring, and this is a spindle. And here is a joint bearing where it has been pivoted. Then how does it work? So when the moving system is deflected, it gets wounded on the other one, gets unwounded. One spring is wounded, it is getting winded. Other one is stretching. The result is controlling torque, whose magnitude is directly proportional to the angle of deflection as it will move to this particular position. So it is proportional to this deflection theta. The deflecting torque is proportional to the current, that is TD is proportional to, that was the deflection torque, is proportional to the current which is passing through this, and TC as well. TC is directly proportional to the deflection angle. This TC will be proportional to the theta of the pointer. So at the steady state, when this pointer will be balanced, at that case, the deflecting torque will be equal to the controlling torque. TD equals to TC. Hence, it becomes, if the deflection is directly proportional to the current, the scale is linear. If the deflection is not directly proportional or having some square relationship or some other relationship with the current or with the quantity being measured, then the scale will be non-linear. Next method of producing the controlling torque is gravity control method. In this method, no springs are there. Only a counterbalance weight is being provided to balance or to control the deflection. So in gravity control method, a small weight is attached like this. This is balance weight. So there are three positions which have been depicted over here. This, and this. So this weight basically balances the deflection of the pointer which is attached to the spindle. So this is how it will be working. So this is a spindle, control weight. The weight components or weight will be directly pointing towards, perpendicularly downwards. The component of that is W sin theta and W cos theta, will be like that. And if this deflection angle is theta, this angle will also become theta. So this is how it will work. So in a gravity control method, a small weight is attached to the spindle of the moving system. Due to the gravitational pull, a control torque acting in opposite direction to the deflecting torque is produced whenever the pointer tends to move away from its initial position. So as the starting position is there, as it will be moving towards any other position, it will try to counterwalk. So in this case, the TD is directly proportional to the current. Here in the case, TD is again proportional to the current, and TC is proportional to the sine of the deflecting torque. And the scale becomes non-linear, that is cramped scale. So in this case, the problem that arises is the non-linearity. Now comes the damping torque, that is restoring torque. So damping torque minimizes the oscillations. What happens when the pointer tries to move in a specific direction like that? So what happens at a certain point when it tries to become steady, when TD becomes equals to TC, that is controlling torque becomes equals to deflecting torque, it will try to oscillate at that point like that. So to minimize these oscillations, because we have to take the correct reading, so we have to minimize these oscillations, and that minimization is done using the damping torque. The damping torque minimizes the oscillation of the pointer about final steady state deflection and makes it steady. In the absence of this torque, the pointer continues oscillating to its final position after reaching final position. So depending upon the magnitude of the damping, it can be classified for underdamped, overdamped, and critically damped. So there are two specific methods which have been depicted over here: air friction and eddy current damping. There is one more, that is fluid friction damping, that we will have an overview of that. So air friction damping is something like that there is a piston which is moving in a hollow cylinder. This is a hollow cylinder, air chamber, and this piston basically is connected to the spindle. As the spindle moves, this piston is also moved, and it tries to create a vacuum in this air chamber. As the point will be balanced, or it will reach to a final steady state, what will happen? It will try to minimize the variation in the pointer's position. So there is a light aluminum frame which is attached to the moving system. This piston moves in an air chamber closed at one end at the time of oscillation of the moving system, or pointer about its final steady state. If the piston is moving into the chamber, the trapped air gets compressed and the pressure opposes the motion of piston, and therefore the moving system or the pointer. Similarly, if the piston is moving out of the chamber, the pressure is closed in this chamber is falling and overcomes and becomes the less air pressure of the outer environment, the outer part of the piston. So again, motion is thus again opposed, oscillations are damped. This is how the air friction damping works. Next is your eddy current damping. Eddy current damping is basically inspired by the eddy currents induced in the circuit. Now, how does it work? So, if we see this is a damping magnet, this is a spindle and a pointer connected to this spindle. This damping disc basically is used with this damping magnet. This is how it looks. This is a pointer, this is aluminum firmer, here are the permanent magnets which are attached over here. This is eddy current situation, and this movement of the coil in a permanent magnetic field is in this direction. It tries to keep, if these magnetic field lines are like that, this is outwards inside there, and this is outwards. Magnetic field direction which have been induced in this disc is inwards, and this is outwards. So direction of eddy currents will be like this, opposing the motion of the coil. So as this particular disc is basically having eddy currents, those are the circular surface currents, which will be trying to oppose the motion of the coil. So here The description of that is aluminum frame or damping disc is mounted on the spindle and free to rotate in the magnetic field provided by the damping magnets. Since the damping disc is rotating with the spindle, EMF is induced in the disc. That is because of the Faraday's law of electromagnetic induction. Since it is a complete closed circuit, the eddy current will form in a circular fashion. So on this surface, there will be eddy currents like that. These eddy currents will be basically induced in a damping disc. Interaction between these eddy currents and the magnetic field develops a specific force on the damping disc, which opposes the movement of the sheet and thus provides the damping of the oscillations of the pointer. So this is how the eddy current damping works. Next is your fluid friction damping. In a fluid friction damping, basically a piston or disc is inserted into a damping oil, which is having some specific viscosity. So friction between the disc and the fluid is used for opposing the motion. Now, damping force due to the fluid is greater than that of air due to the more viscosity, and it consists of a vane attached to the spindle, which is completely dipped or submerged in oil. The frictional force between the oil and the vane is used to produce the damping torque in this case, and this opposes the oscillating behavior of the pointer. Now comes a very important instrument, that is permanent magnet moving coil, PMMC. So PMMC, as the name indicates, PMMC is basically telling you about that it is using permanent magnets and a coil in which the current will be flown, and due to that flow of that current, what will happen? The movement of the pointer will take place. So basically it consists of a magnet, which is a stationary, permanent stationary magnets. Moving system consists of a spindle attached to the rectangular aluminum frame. A coil made up of a thin copper wire is wounded over the frame. The current to be measured is passed through this coil. A soft iron core is placed in between the space between the aluminum frame, which is core is stationary and provided to reduce the reluctance of the magnetic path between the two poles of the permanent magnet, that is north pole and south pole. Now there will be spring control provided over here. Two spiral springs are mounted on the spindle to produce the control torque, and control spring also serves as additional purpose and act as a control lead. Pointer is mounted on a spindle. Mirror is provided below the scale to avoid the parallax, and the spindle is supported by the jeweled bearings. The working will be depicted with the diagram itself. So this is the diagram that we see over here. This is soft iron core. These are the control springs, the spindle. This is a spindle. This is a calibrated scale on which a pointer is mounted. And here, north and south poles. These are permanent stationary magnets. This is soft iron core within this coiling. And this is a moving coil. So this is another cutaway which could be described, where this is a zero position control. This is a pointer which is moving. Control spring. Here are counterweight, pole shoe, moving coil or aluminum frame, and this is a soft iron core. This basically uses the counterweight mechanism, gravity control method, and here it is spring control method. So how does it work? When a quantity of current to be measured is passed through this coil, what will happen? These are permanent magnets. We'll be creating a magnetic field. Then in this magnetic field, a current carrying conductor is placed, and to reduce the path of reluctance, we have used this soft iron core. As it will be done, a circular force will be developed, rotational force will be developed, the coil will be moving. As the coil will move, the spindle will move, rotate. We'll try to move this pointer on a calibrated scale. Spring control method basically restricts this motion, and at a steady state, TD will be TD equal to TC, that is deflecting torque equals to controlling torque. The spindle becomes, or the pointer becomes steady. So this is how it works. So this is the construction and basic description of the permanent magnet moving coil instruments. So Basically, permanent magnets are stationary, moving systems, rectangular aluminum frame, coil of thin copper wire, soft iron core, spiral springs, and pointer and mirror. So this is basic construction of PMMC. Now, what could be the possible sources of error in PMMC instruments? Basically, permanent magnets with the time loses their magnetism property. So first error is weakening of permanent magnet due to aging and temperature effects. Then weakening of springs due to aging and temperature effects. As the time changes, their spring constants are changed. Change of resistance of the moving coil also changes with the temperature. If it is kept in a different temperature environment or as the heating takes place. So what will happen? By the time the resistance of the coil changes. Then advantages are scale is uniform. Here proportional deflecting torque is always proportional to the current which is being measured. So this is uniform scale for the instrument. Power consumption is very low because very thin copper wire structure is used for coiling, and single instrument can be used for different current and voltages ranges. We can use different voltage and current ranges or measure different current and voltage ranges by using simply various shunt and series resistances. The torque weight ratio of this instrument is high, so provided very high accuracies. Demerits are only could be used for DC supplies where alternating currents are involved. This instrument cannot be used. And the cost of the instruments are heavier than the moving iron instruments. So this is the disadvantage of that. Now, if we want to use these PMMC instruments as ammeters and voltmeters, how do we specifically implement them? So that is what depicted in this topic. So this is a PMMC instrument. This is an instrument which is having a resistance Rm, meter resistance. The current flowing through this is Im, meter current. And this is a shunt resistance, Rs. And this is the current flowing through the shunt, that is Is. The main current was I, which was to be measured. And the range of these instruments, this will also describe that how the range of the instruments could be enhanced. So an ammeter, if we want to take a measurement of current, then obviously we need to use ammeters, and ammeters are always connected in series circuits. So are connected in series with a circuit branch and measures the current flowing through this. The DC ammeter employs the diason wall movements. An ideal ammeter would be capable of performing the measurements without changing or distributing the current in the branch. But in actuality, ammeter would possess some internal resistances. There will be some resistances involved in that. So what happens in the case? The coil winding in PMMC is very small and very light. They can carry only very small currents for you can say microamperes or milliamperes range. So if we want to measure a large current, what happens for that? If large current is passed through directly through a meter, the coiling will burn out. So in that case, we need to use a external shunt resistor to connect with the meter movement. So only a fraction of the total current will pass through the meter, and the remaining is passed through the shunt resistances. For this case, we will consider that the voltage across this meter, that is Vm, is equals to voltage across this shunt resistor, and these two are connected in parallel, so these will be equal. So Vm equals to V shunt. So if we write Vm is current through meter multiplied by the resistance through meter, and current through shunt resistance multiplied by the resistance of the shunt. So from here, we specifically see that this Is is I minus Im. So that is what has been written. Ish equals to I minus Im. Then from here, if we put the value, Im equals to I minus Im RSH. So if we want to enhance the range of the meter, then this shunt needs to be implemented. So from here, we can calculate the value of this RSH, that what shunt resistance is required to extend the range. This is the I is the current through which we need to measure. So this is how we can calculate the value of shunt resistance. Now comes DC voltmeter and how the DC voltmeter range could be enhanced. So DC voltmeter, basically voltmeters are always connected and across any resistance or for any devices where voltages are to be measured, those are connected across. So here a voltmeter is always connected in parallel with the element being measured and measures the voltage between the points across which it is connected. Most DC voltmeters employs these PMMC meters. Now, the same situation, if the voltage is higher, the current capacity of the coil is very limited, and if the voltage is higher, the higher currents will be applicable. So how to avoid that particular situation so that the coil does not burn out? A series resistance is implemented in conjunction with the meter, and this is how it will work. So as you can see, for enhancing the range, the multiplier resistance RS or RS series resistance is inserted over here. This is meter resistances IM, and here IM is equals to I itself, the current which was being supplied by the source, and voltage is V is the voltage which is connected across. From here, if we implement the KVL equation, so this will be the equation. RS equals to V minus IM RM over IM. Multi-range voltmeter could be connected like that. Number of series resistances are connected to the circuit, and whatever resistance needs to be inserted, that needs to be connected with the help of a dial. And this is how the sensitivity of a voltmeter is defined. 1 upon IFST, ohm per volts. So this is all about the PMMC instruments and their range, their use as a meter and voltmeters, extension of their ranges. So feel free to ask any doubts if you have regarding this. Thank you.